Alright, so today we're going over chapter 10, section 4, inscribed angles and polygons. So, inscribed angles and intercepting arcs are an angle whose vertex is on a circle and whose sides contain chords of a circle, an arc that lies between two line, rays, or segments. So you guys have an idea. This right here is a chord. So these two are chords actually. This is the inscribed angle. So in other words, you can put it as the vertex of both of the chords. So in other words, a vertex. And the vertex has to be, is on the circle. And remember, an inscribed angle is not a central angle. That is not how you spell remember. I'm sorry. So remember, the central angle, which is the one we've been talking about before, central angle is different than the vertex at the center. So the central angle has the vertex at the center. So the central angle would be around here-ish, I guess. And this is the inscribed angle. So the inscribed angle has a vertex on the edge of the circle, and the central angle has a vertex in the center of the circle. Now we have theorem 10.10, which is measure of an inscribed angle theorem. So the measure of an inscribed angle is 1/2 the measure of its intercepting arc. So remember, I'm just going to write it again. The central angle is equal to the arc, while the inscribed angle is half. So inscribed angle is half of the measure of the intercepting arc. So if we were to do the arc from right here, which is the center, the arc would equal the center angle, but it's half of the inscribed angle. So this is half of the arc. It is important that you guys remember the distinction. Now we have the measure of angle ABC, which is half of the arc AC, and then we have the arc AC will be twice the measure of the angle ABC. So it's important that you guys know and remember that they can be flip-flopped. So theorem 10.11 is inscribed angles of a circle theorem. So if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So what I was trying to say is angle 1 and angle 2 are going to be congruent, because if you follow their path, they land in the same arc. So angle 1 and angle 2 both have arc AB as their measure. So if you guys are able to find just one angle, you guys can equal the other one to it, because the angle will be half of the arc, like we learned in the other one. The vertex is at the edge of the circle and is in the same arc AB. So you would solve for angle 1 and angle 2 by the same arc, which is this case is arc AB. So this is for both 1 and 2. So inscribed polygon and circumscribed circles. Inscribed polygons, key important, they are inside polygons. A polygon with all of its vertices on the circle. So an inscribed polygon could be this triangle right here, because all the vertices are inside of the circle. And then we have the circumscribed circle, which is the circle that contains the vertices of an inscribed polygon. So the inscribed polygon is the triangle or the quadrilateral right here. And the circumscribed circle, I have a hard time saying that word, is that red circle outside of the polygons. So the circles here are circumscribed. Circumscribed we can think of as kind of they're cutting it out, that piece, or they're putting something into space about the triangle or the quadrilateral. So we have theorem 10.12, which is inscribed right triangles theorems. So they're all kind of derivative or denomination from the previous ones. So let's just read what it is first. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. And then we have the conversely, if one side of the inscribed triangle is a diameter of a circle, then the triangle is a right triangle, and the angle opposite of the diameter is a right angle. So we have in this case, we have a few things that we can talk about this circle and this triangle. So they're telling us measure of ABC is equal to 90. If and only if, so this is the most important part, AC is the diameter. Now, AC being this line right here, goes from edge to edge in a straight line, and it crosses through the center, so it is a diameter. Also, notice that this entire thing, if that's a diameter, this is a semicircle, so it would be 180 degrees. Why am I pointing this out? As you're solving for different sections of the squares, so like I was saying, as you solve for the angles in the circle around 180, it is important to know what parts and what sections are equal to what. As in this case, we have different angles and different theorems. This one is based on the diameter, so you're able to tell half the circle is already 180. And then the remainder, the other half is where the triangle is. So it's going to be a little easier to figure it out because you can divide different things. Now I marked ABC as a 90 degree just so you guys have the full diagram. But this is as much as I'm going to talk about this circle right now. So here we have theorem 10.13, inscribed quadrilateral theorem. So a quadrilateral, I'm just going to underline it, can be inscribed in a circle if and only if its opposite angles are supplementary. So this is just a quadrilateral. You could have a bunch of different quadrilaterals. It could be a square, rectangle, parallelogram, rhombus. As long as it's a quadrilateral, it will make sense. Now, it is important to note that if and only if the opposite angles are supplementary. So what does this mean? That means angle 1 and angle 3, when added together, need to equal 180. As well as, for example, 2 and 4, when added together, need to equal 180. So that's what it means by the opposite angles must be supplementary. If they're not supplementary, then the quadrilateral is not inscribed properly into the circle. So this is just a useful fact. An angle inscribed in a semicircle is a right angle. But keep in mind, this is the diameter. So it's one of its theorem 10.12, the inscribed right triangle theorem. But it is good to know. If this is 90 degrees, because the hypotenuse is the diameter, or if the hypotenuse is the diameter, then you know that angle 1 or the opposite angle of that line is going to be a right angle no matter what. So they want us to find the values of x and y in circle 0. Now both of these circles are called, circle O, not 0. It's fine. So they're telling us for circle A, we have angle 20 right here. And we have two arcs. We have this arc highlighted right here. We have this arc highlighted right here. And they want us to find angle Y, which is going to be half, basically, of whatever this whole thing is. Well, angle Y is that whole thing, so we can figure it out. Now, if we have 20, we can find x. If you guys remember, because this is an inscribed angle, it's going to be doubled. So our x is going to be 40. Now, our y is going to be a little different because it encompasses, if you notice, our y is both of these arcs together. So we're going to first have to add them together. So I'm going to do 110 plus 40. We get 150. Now, because 150 is the entire arc for where angle y is, I actually have to do 150 divided by 2 in order to find y. And when I do that, I get that my y is actually 75 degrees. All right, so for example B, we want to find x and y. Now I'm going to go ahead and highlight where x is, so it's going to be this red area. And the y is going to be this entire thing. So we have to figure out what's going on. Now, the first thing I can figure out is that if you notice, we have a triangle right here. I'm going to go ahead and just kind of highlight it in green. And notice the hypotenuse of that triangle is a diameter. So with theorem 10.11, the inscribed angles of a circle, well, not that one, the diameter one, we know that our angle y is actually going to be 90 degrees because of that theorem. Now let's figure out how we're going to do with x. Now x is this section right here. I will do it in red again so we mark it. X is this section right here. So it's going to be this arc. But how are we going to find that arc? Well, we have given this this angle right here, which is also shares the same endpoints of the x arc. So we can just say, well, that arc is going to be 40 because it's going to be 20 times 2. And because that they share the same arc, angle x and angle 20, we know that our angle is actually going to also be 20 degrees because it's in they share the same arc. Now, other things I want to point out before we move on, but this is it. That's it. That's the answer. It's good to always highlight what you have and what you're missing and where the endpoints are. Since you have the diameter, this is also going to be a full 180 degrees. Just so you guys remember. We don't need that information to solve for this. This is just kind of more so you guys understand what's going on. So for example C, they want us to find, again, x and y. And if you notice, they're going to be, we have a triangle inscribed into this circle. So the few things we can figure out. This angle right here, we can figure it out. It's going to be half of 140 because 140 is its arc. So we know this angle is going to be 70. Now, knowing that that angle is going to be 70, we're actually going to be able to find the rest of the information. Because the triangles are always equal to 180. If I do 70 plus 60, I get 130. And if I do 180 minus 130, I'm able to get that this last angle is 50. Now, why is that important? I want you guys to notice 60 right here goes with arc x. So x is going to be 2 times 60. So it's going to give us that x is 120 degrees. Now for y, it's going to be, again, based on that 50 that we just found. And it's going to be double. So y is going to be 2 times 50, which gives us that our y is 100 degrees. So for D, they want us to find x and y. So some important things. They're telling us that these two segments are congruent right here. They're telling us that they share this one line, and that one line is a diameter. So with theorem 10.12, it's inscribed right triangles. We know that this angle is going to be 90 and this angle is going to be 90. Now, because we know that these are going to be congruent, we can actually go ahead and try and solve this. Now, first things first, this is half a circle and this is the other half. So we know this entire thing is going to be 180. So we can figure out the remainder of the circle. So this remainder is 100. Now keep in mind our x is facing the segment that it's already given. So if we do, our x is going to be half of 80, or in other words, 80 divided by 2. So our x is actually going to be 40. Now our y is facing this entire thing. So we have to figure out what's going on. Now we know that the corresponding angles, chords theorems, these two are the same and they're 90 degrees. So we're left that this theorem, this chord right here is 100. This is from the last section. So because that's 100, I can say that y is half of 100. So we know that our y is going to be 50 degrees. All right, example 2 is a proof. So given circle 0 equals circle P, arc AC equals arc AB, we got to prove that the two triangles are congruent. Now I'm going to make a new slide with these statements and the reasons, guys. Now I'm going to write out all of the statements and you guys just write down the reasons. So statements and then reasons. We have the first statement. circle O equals circle P. And we have the arc AC equals arc AB. Obviously, that's the given. That's the only reason I'm going to give you. I'm going to keep writing 2, 3, 4, 5, 6, 7, 8. I'll give you guys a moment to try and answer them, and then I'll fill them in. So we have statement 2. AC is equal to AB. 3. Angle CEA is half of arc AC, as well as angle BDA is equal to half of the arc AB. Now we have the fourth statement. Angle CEA is equal to half of the arc AB as well. So we can say that angle CEA is equal to angle BOA. And our sixth statement would be angle B would equal 90 degrees, as well as angle C will equal 90 degrees. We have the seventh, which is angle B is equal to angle C. And lastly, we have the triangle ABD is equal to triangle ACE. So I give you guys a few seconds. I pause the recording to do that. Now, for statement 2, we have congruent, corresponding, chords theorems for that one. For 3, we have the measure of inscribed angle theorem. For 4, we have substitution. As well as for 5 is substitution as well. Now we have 6, which is the inscribed right angle theorem. I'm going to put RT for right. Triangle theorem, sorry, not angle. Then we have 7, which is substitution. And lastly, those two triangles are congruent by the angle side. Now, guys, there's multiple ways to make sure that to show that these triangles are congruent. This is just the way I did it. You could have done it differently.